In the last few classes, we were discussing on the gas power cycles, and we have discussed on the thermal efficiency of Otto cycle. Now we will show how to calculate the work output and the mean effective pressure for the air standard Otto cycle. Okay. So work output, as we know, that is net work output for the cycle is the area enclosed by the diagram. So basically, if we draw the diagram, the PV diagram, then the area enclosed by the diagram will be the net work output. So we will draw the diagrams. So I am drawing two lines on the volume axis. So one is representing the top dead center, another is representing the bottom dead center. So we are trying to draw the PV diagram confined within the top dead center and the bottom dead center. Again, we will draw one line corresponding to the pressure, which is representing the atmospheric pressure. So that is basically the inlet pressure. So this is the inlet pressure. This is the pressure side pressure, and this is the volume unit, maybe meter cube or maybe meter cube per kV, that is specific volume, and the pressure is in either bar or kilopascal. Here now we will draw the PV diagram. So PV diagram will be like this. Now we will try to draw the PV diagram from this point. So it is the compression process. Next is the heat addition process. Next is the expansion process, and finally it is the heat rejection process. Okay. Now this area is the work output. So in the PV diagram, this is W net. So that is what is equal to integral P dV. And you know from your thermodynamics, basic thermodynamics, that what is the work output for this process? W net is equal to. Now if I mark the points here, so the inlet is 1, then after compression it is 2, here it is 3, and here it is 4. So 1 to 2, isentropic compression. Then 2 to 3, constant volume. Heat addition. Constant volume means isochoric. Next, 3 to 4, again, isentropic process. Expansion. And 4 to 1 is constant volume heat rejection. That part we have already seen. Next, this W net is equal to basically under these two curves 3 to 4 and 2 to 1. So if I integrate these two curves, that means the area under these two curves 3 to 4, it will be what? It will be this full area. And we know that that is equal to what? This full area, shaded area, that is equal to P3 V3 I can write in terms of the total work, or I can write in terms of the specific work. So here I am writing total work. So it is V3 minus P4 V4. So I will use this symbol V cut. V cut is for the total volume, and capital V I will be using for velocity. So P3 V3 minus P4 V4 by gamma minus 1. This is for the isentropic expansion, isentropic process, the area under this. Okay. Next, the area under the 2 to 1 or 1 to 2 process, what is that? Area under the 1 to 2 process is this one. This green part. And since this process 1 to 2 is similar to that of 3 to 4, only thing is that it is compression and 3 to 4 is expansion. So compression, it will be negative. And therefore, we can write that for 2 to 1, the work output is minus P2 V2 minus P1 V1 by gamma minus 1. So the green shaded area is this one, and the line shaded by blue color area is this one. So the net work output for the cycle is the densely shaded by the blue color, that is the area enclosed by the cycle diagram, that is equal to this P3 V3 minus P4 V4 divided by gamma minus 1 minus P2 V2 minus P1 V1 divided by gamma minus 1. So that is the work output. And you can go for further calculation. Again, we can write that from the isentropic diagram, we know from the isentropic process, P2 V2 by P1 V1 is equal to what? Is equal to V1 by V2 to the power gamma from the isentropic process equation. That is P1 that comes from what? PV to the power gamma is equal to constant. From that, you can get it. And this is same as equal to V4 by V3 to the power gamma, because 1 to 4 and 2 to 3, they are constant volume processes. So V4 by V3 to the power gamma. And therefore, it is same as P3 by P4. So therefore, we can write, again, we know that this is equal to, this V1 by V2 is equal to R, that is volumetric compression ratio. This is same as V3 by V4 by V3. Therefore, what we can write is that P2 by P1 is equal to P3 by P4 to the power, is equal to R to the power gamma. Okay, so that we can get. Okay. Now target is to calculate the work output. So this is the first step that we are doing. Next, what we will do is, we will again write, we will define a quantity called the pressure ratio. Here you see that from 2 to 3, there is a change of pressure. So from 2 to 3, the pressure increases. So I can write that P3 P3 by P2. Again, it is same as P4 by P1. As we can see, because this P3 by P2 is same as P4 by P1. That we can write as that we can define as RP, that is pressure ratio. Because you see that P3 by P2 and P4 by P1, you see that between these processes 1 to 2 and 4 to 3 or 3 to 4, basically these are isentropic processes between two constant volume lines. Therefore, this ratio of pressure between 1 and 2 and between 4 and 3, they will be basically in the same ratio by, they can be represented by the same ratio of volume. And since volumes are same, therefore, the pressures can be written, that is ratio of pressure can be written equal. That is the pressure rise from 2 to 3 and pressure rise from 1 to 4, they will be basically same. So that you can show, like, say between 1 to 2, what is the pressure that is process P1 V1 to the power gamma is equal to P2 V2 to the power gamma. Okay. Again, we can write that P3 again we can write that P4 V4 to the power gamma is equal to P3 V3 to the power gamma. I have written in this way because V1 is equal to V4 and V2 is equal to V3. So if I divide the first equation by the second equation, then that volume terms will cancel and the pressure terms will only remain. So if I divide it like this, that means the left hand side I divide by the left hand side of the second equation, and the right hand side of the first equation I divide by the right hand side of the second equation. Therefore, it will be P1 V1 to the power 4 by P4 V4 to the power 4 is equal to P2 V2 by V3 whole to the power gamma. I'm sorry, here I have written 4, it will be basically gamma. So it is gamma, gamma. And we know that V1 is equal to V4. So V1 by V4 will be 1 and V2 is equal to V3, so it will cancel. Therefore, it will be P1 by P4 is equal to P2 by P3. So that is written here. P3 by P2 is equal to P4 by P1. So this one is equal to basically 1 by Rp. So therefore, if we try to write, now our target will be to calculate this quantity. So what is that? W net is equal to what? P3 V3 minus P4 V4 divided by gamma minus 1 minus P2 V2 minus P1 V1 by gamma minus 1. So if we take this 1 by gamma minus 1 out of this and also take say P1 V1 out from this common P1 V1, then it will become P3 V3, means all the terms will be divided by P1 V1. Minus 1. So this is the last term. Okay. Now, therefore, W net, you see that our aim is to calculate the quantity in terms of the inlet property and the volume ratio or the pressure ratio. So here it is P1 V1 by gamma minus 1 whole multiplied by this quantity. So I can write this as P3 by P1 multiplied by P3 by V1 minus P4 by P1 multiplied by V4 by V1 minus P2 by P1 multiplied by V2 by V1 minus, I'm sorry, this is plus 1 because here it was a minus and here it is another minus. So it is, the last term will be plus. So this will be plus 1. Okay. Next, we will replace those values. So as we know from this top that P3 by P1, again now we will try to write what are the quantities. So P3 by P1, here it is P3 V3 by P1 V1. What is that? We can write P3 by P2 multiplied by P2 by P1 multiplied by V3 by V1. Okay. What is P3 by P2? P3 by P2 is equal to RP here. So it is RP. Next, P2 by P1, what is that? P2 by P1 is equal to R to the power gamma. P2 by P1 is equal to R to the power gamma. So R to the power gamma. And what is V3 by V1? V3 by V1. So V3 by V1, we can write V3 is what? You see that V3 is equal to V2. So we can write V3 by V1 is equal to V2 by V1 because V3 is equal to V2. And what is V2 by V1? V2 by V1 is equal to 1 by R because V1 by V2 is equal to R. So V2 by V1 is equal to 1 by R. So this will be multiplied by 1 by R. Therefore, it is Rp into R to the power gamma by R. The first term. And what is the second term? The second term, we see that this term here V4 is cancelled with V1 because V4 is equal to V1. V4 is equal to V1, so they will cancel. And therefore, the second term will be P4 by P1. And what is P4 by P1? Simply, you see that P4 by P1 is equal to RP here. So the second term will be RP. This term will be basically RP. This term is what? This term is RP into R to the power gamma minus 1 or RP into R to the power gamma by R. And what is P2 V2 by P1 P1? P2 V2 by P1 P1, you see that the third term P2 V2 by P1 P1, P2 V2 by P1 V1 is equal to P2 by P1 multiplied with V2 by V1 is equal to what? P2 by P1 means what? P2 by P1 means this one. So P2 by P1 is equal to R to the power gamma. Right? This is R to the power gamma. So the first term is R to the power gamma. And what is V2 by V1? It is again 1 by R. So it is R to the power gamma minus 1, or you can write simply R to the power gamma by R. So this is R to the power. The third term, this third term is basically R to the power gamma minus 1. And this is plus 1. So therefore, we can write the work term W net is equal to P1 V1 by gamma minus 1 whole multiplied by Rp to the power Rp multiplied by R to the power gamma minus 1 minus Rp minus R to the power gamma minus 1 plus 1. Okay. Next, we can take from this R1, sorry, Rp as common from these two. Therefore, it will become P1 V1 by gamma minus 1 whole multiplied with Rp R to the power gamma minus 1 minus 1. So it is Rp I am taking out. So it will be R to the power gamma minus 1 minus 1 because here it is Rp. Minus, if I take 1 common from this, so it will be minus 1 common. So it will be R to the power gamma minus 1 minus 1. Where we can see that these two quantities are identical. Therefore, we can write it is equal to W net is equal to, in the next page, I can write W net is equal to P1 V1 P1 V1 by gamma minus 1 whole multiplied with R to the power gamma minus 1 minus 1 multiplied with Rp minus 1. So if I take Rp, R to the power gamma minus 1 minus 1, then it will be Rp minus 1. So this is the expression for work output, net work output for the Otto cycle. Okay. Next, we will try to derive what is the mean effective pressure. As we know from the definition of mean effective pressure, what is that? Mean effective pressure. Mean effective pressure. So P mean effective pressure. So MEP or basically MEP simply. So, or you can write simply PM. It means mean effective pressure is equal to, what is that? W net divided by the swept volume that we have derived, that we have defined. So the definition is net work output divided by swept volume. Okay. Now what is Vs? Swept volume is equal to the volume at TDC minus, I'm sorry, volume at BDC minus volume at TDC. So this is V2, V1 minus V2. Again, we know that what is the relation between V1 and V2? V1 is equal to R into V2 because V1 by V2 is equal to compression ratio R. Therefore, V1 is equal to R V2. Therefore, we can write V2 is equal to V1 by R because we want to calculate or we want to express V2 in terms of V1 because V1 is the inlet condition. So all the quantities we will try to represent in terms of the inlet quantities. So V1 we will keep it minus V1 by R. Therefore, if I take 1 by R, then it will be minus 1 by R. So it will be, V1 by R. So it will be R minus 1. Simply. So Vs is equal to this one. Therefore, PM or mean effective pressure is equal to W net divided by Vs. What is W net? W net is this one. That is P1 V1 whole multiplied with R to the power gamma minus 1 Rp minus 1 divided by gamma minus 1 multiplied by 1 by Vs. So 1 by Vs is equal to therefore R by V1 multiplied by R minus 1. I have just taken the reciprocal of Vs. Okay. So therefore, you can write that this V1 will cancel here and here. And therefore, this quantity Pm, mean effective pressure, is equal to P1. So it will be P1. Let me write it in a different way so that it will be easy for you to understand. So P1 multiplied with, now here it is R multiplied by R to the power gamma minus 1 multiplied by Rp minus 1. So R multiplied by R to the power gamma minus 1 multiplied by Rp minus 1, and in the denominator it is gamma minus 1 whole multiplied with R minus 1. So this is R minus 1 and this is gamma minus 1. Okay. Now we can highlight this. So this is the mean effective pressure. Okay. Now you see that in this mean effective pressure, all the quantities except the pressure on the right hand side are all ratios. This one. R is compression ratio. Yes, yes. Problem can be say about 10 marks also, or say 7, 8 marks, depending on the length of the problem. So it can be, say, for example, simple Otto cycle efficiency calculation. So the compression ratio is given, and say the particular working fluid, either say CO2 or air, is given. So accordingly, you can understand what will be the value of specific heat ratio. So you can calculate it simply by one step calculation, right? So Otto cycle efficiency will be basically thermal efficiency of the Otto cycle is equal to 1 minus 1 by R to the power gamma minus 1. So as you know compression ratio and you know the fluid, you can calculate this efficiency within one step. So that can be say 3 marks maximum, right? Now if it is work calculation, then it requires a longer process, so it will take time. Therefore, the marks will accordingly increase. For example, it can be say 5, it can be 7 marks, or like the 7 marks, 8 marks, or mean effective pressure calculation. It can be say total of say 10 marks to means taking efficiency, work output, etc. So the problems can be actually of different types. So for example, heat input is given and the compression ratio is given. Okay. Say for example, a problem can be like a heat input given. Say heat input given, Q in, and the compression ratio given, and the working fluid is given, so gamma is known. Okay. So uh, you are required to calculate the, say, work output. Work output means work output per unit mass. Obviously, here you cannot calculate the total work output. One thing you have to remember that depending on the data that is given, you can calculate some quantity or you cannot calculate some quantity. So if the data contains the extensive properties, that is some total properties like total heat transfer or total mass of the air is given, then only you can calculate the total work output. Otherwise, if this is given, like say heat transfer per unit mass, and nowhere the mass or the reference or the information about the mass is not given, in that case, you cannot calculate the extensive properties like total work output or total heat rejection, etc. You cannot calculate. So in that case, you will be always able to calculate the quantities per unit mass only, because mass is not given in the problem. So you will be able to calculate only per unit mass quantities. Okay. So here you see that if these three are given, so if the work output is to be calculated, how to calculate that work output? Can you tell? W net is to be determined. Okay. Now you see that from these two quantities, you can calculate the efficiency. Thermal efficiency you can calculate, right? And thermal efficiency is equal to W net by Q in. So Q in is given here and efficiency you have just calculated. Therefore, you can determine what is W net. Without this lengthy work means formula, you can calculate this. So it depends on what is the type of problem, what are the information that are provided. Depending on that, the length or the marks of the problem will definitely vary. Say, for example, this problem, work calculation, it can be justified, say, for example, 3 marks, 3 to 5 marks maximum, isn't it? You see that only 2 steps are required. One is to calculate the thermal efficiency. Another is to calculate the work output from the ratio of from this thermal efficiency is equal to work network by Q in. So from this is a 2-step calculation. So we can justify only 3 marks for this, not more than that. So if it even if it is say 5 marks, it is more than enough. So it depends on what are the information given and what are the information to be calculated. What are the quantities to be calculated? Okay. Okay. Are you getting my point?
Yes, sir.
Yes. So when we will solve problems, so we will show the types of problem. What are the types of problem that can come? And accordingly, we will try to solve the problems in a shortest way, so that you can justify the marks. That means it may not appear to you that the marks is less compared to the effort that I am putting. So that will not appear to you. Okay. So many things are to be checked during solving a problem. So whether some quantities that are asked in say some problems can be a wrong one, means some quantities are asked which you may not be able to calculate. If the problem is wrong, then you may not be able to calculate the quantity that is asked. So you can justify or you can judge from some analysis that whether this can be solved or not. Okay, we will show that during our discussion on the problem solving. Okay. Okay. So,
Okay, sir.
yes. So, we have shown the quantities like this. That is, work efficiency. Efficiency is equal to 1 minus, let me rewrite it for the sake of completeness. Efficiency, thermal efficiency is equal to 1 minus 1 by r to the power gamma minus 1. So this is thermal efficiency. Then we have calculated the work output, and then we have calculated the mean effective pressure. Okay. So these quantities can be determined this way. Okay. Now we will move towards the next cycle, that is the diesel cycle.